Hello there, this is Shoot Socrates. Welcome to Multivariable Calculus. This is video number 22 in our series for Math 5C at Pasadena City College. So in our previous video, we started on the concept of spherical coordinates. We introduced how to go back and forth between Cartesian coordinates and spherical coordinates, rho, phi, and theta, and what they meant. We saw some basic surfaces in spherical coordinates when we set one of the coordinates equal to a constant and we let the other coordinates be whatever they want to be. So we found spheres, we found cones, and we found half planes. And we put them together so that we could find or create solids in spherical coordinates, which we called spherical bricks. So we saw several examples of them. We saw a solid ball as opposed to a sphere, so like a billiard ball, something which is solid on the inside. And we can take portions of a solid ball. You can take a half ball or the portion in the first octant where everything is positive. We saw ice cream cones. Okay, so you can have a solid cone on the bottom and a sphere on top. Okay, so today we are going to continue, because we still have a lot of work to do. We are going to learn how to find the volume differential, dV, in spherical coordinates. And of course, it's very important because we're going to need it in order to perform our integration. Okay, so that will be our agenda for today. We will continue on page 107. Okay, so as I said in the last video, it's a little bit like what we did in chapter 2, where we converted the area differential dA, which is usually dx, dy in Cartesian, into rdr d theta. And of course, we also just did triple integrals in cylindrical coordinates, so this showed up once again. So what we're going to do now is we're going to look at the volume differential dV, which is usually in dx, dy, dz in Cartesian, and maybe rdr d theta dz in cylindrical, but it's going to be very, very different in spherical coordinates. Okay, so here's our setup. We're going to use the spherical brick that we created last time. Rho is going from A to B, phi from alpha to beta, and theta from mu to nu. All right, so m and n. Okay, so how do we create a triple integral? Okay, it's all about partitions, subdivisions. So as usual, we're going to subdivide AB into L subintervals. So the width is denoted delta rho, B minus A over L. Similarly for alpha beta, that's for phi. So delta phi is beta minus alpha over m. And for theta, we will have nu minus mu over n. Okay? And as usual, we're going to partition the intervals. We will start at A as rho 0, and then rho 1, rho 2, skipping by delta rows until we get to B. Same thing for phi. Phi 0 is our beginning angle alpha, and then add delta phi to get phi 1, delta phi again to get phi 2, and so on until we get to beta. And same thing for theta. We will start with theta 0 as mu on the left, and rotate by delta theta counterclockwise to get theta 1, theta 2, and so on, until we get to the terminal angle, which is mu. All right, so starting with the main spherical brick, we're going to create very small sub-bricks. So our notation for rho will go from rho I1 to rho I. For phi, we will go from phi j minus 1 to phi j. And then for theta, we will go from theta k minus 1 to theta k, right? So basically, we're going to make very small spherical bricks, and we're going to find out that they do look a lot like regular bricks. Okay, so therefore we'll be able to approximate their volumes using regular length, width, and heights. Okay, so yeah, what are these boundary surfaces going to be? We already know that when rho is a constant, we're going to get spheres. Okay, so these will form an upper and a lower sphere, and then we will have cones for phi. So we will have an inner cone and an outer cone. And then finally for theta, we will have the swinging door. So we will have theta flat door, and then it will rotate counterclockwise to the next value of theta. Okay, it would be better if we see this in GeoGebra, don't you think? All right, so here is a teeny tiny spherical brick. Okay, so I believe this is the first time we are seeing this little program that I made, and again, you will have access to that. I hate it when it does that. You expand this box and suddenly your diagram shrinks to nothing. Don't worry, we're going to bring it back. So these are sliders, okay? So these are basically your rho I minus 1 and rho I, phi I j minus 1, phi j, theta k minus 1, theta k. All right, I just gave them more regular names, I guess. Where did it go? I just do standard view, and there we go. We can see it once again, and we can zoom in. Okay, so using these sliders, we can adjust the size of this spherical box. Okay, so yeah, if you want to make it a little bigger, you just adjust A a little bit. Okay, so now it's 2.7. B will adjust accordingly. Okay, so the minimum value of B will be 2.7, and you can change the maximum. You can go beyond 15 if you like. So right now B is at 4. We can make it still a little bigger. Ooh, there you go. It got taller. Okay, so this controls the inner sphere, which is over here. Why am I using my hands? That's your inner sphere, and this is your outer sphere. Okay. Now, what about the phi? Okay, so phi controls the inner cone, which is over here, and the outer cone. So let's make the inner cone smaller in angle. Ooh, see? It got closer to your z-axis. All right, let's check it out. Can you spin a little bit? Yeah, there you go. So it really does look like a wedge of cantaloupe, don't you think? Okay, and we can make the outer phi also a little smaller. Oh, I did not. Yeah, I need to fix it. I should make b phi be at least a phi. Okay, so 0.4, a little too big. But there you go, 0.6. Okay, now zoom in. Okay, so there we go. So those are our inner cone over here and outer cone over here. So that the last coordinates is a theta. Okay, so theta, and these are your wooden doors, your panels. Okay, so this is your angle closer. Oh, wait a minute. Your x-axis is over here. Oh, no wonder theta is very large. So let's make it closer to the x-axis. So yeah, 0.2, and now b theta is too large. Maybe a little small. Yeah, there you go. Okay, so there is this flat plane that is your a theta, and then let's spin it around a little bit. Your b theta is on the other side over here. Zoom in a little bit. Closer, closer. Yeah, there you go. Okay, so that is our spherical brick. Okay. You know what? I don't like how that looks so much. Let's increase the AP just a little bit. Okay, there you go. It's getting a little bit more proportional. There you go. Okay, I like that much better. Zoom in. Closer, closer, closer. I don't know why it's so slow. Okay, there we go. And, just maybe one more little adjustment. Let me make the row a little bit shorter. Okay, 2.7, let's make the outer 4 a little smaller. I think just a little bit, touch bigger than that. Okay, that's pretty close to the proportion I want. Because the point I want to make here is, yeah, when these differences are very small, see how, 2.7 to 3.7, that's still kind of big. Let's make it a little shorter. There we go. Okay. So see how that almost looks like a regular box. Okay, so there's a height to that box. What about the feet? 0.4 to 0.7, that's not too big. Theta, 0.2 to 0.5. Yeah, that's just about close to perfect as I want to have it. Okay, so now we want to understand the volume of this little spherical box. Okay, so how are we going to do that? Well, we're going to use a representative point inside. Okay, if this were a regular box, okay, something that, you know, Amazon would deliver to your doorstep. You haven't done that during the pandemic, right? So you have a regular box, you can have the length, the width, and the height. Okay, so if you look this way, you can kind of tilt your head like this. It does look like just a regular box, right? Maybe slightly squished. Hopefully nothing is broken inside. Okay, so there's definitely a height, and there is a width over here. And if you look this way, oh, there is a depth to it. Okay, so what are we going to do? We have a few more goodies over here. I'm going to hide the boundary surfaces. Okay, so again, we have an upper and a lower, an inner cone and an outer cone. Except it's so narrow that it doesn't feel like a cone, even though it is curved. Okay, and you have a flat plane over here, and also on the other side, you have 6 sides. Okay, so I'm going to hide them one at a time. Okay, so let's say goodbye to this side. Ooh, see it disappearing, and also on the other side, and this side, ooh, and this side, ooh, and how about you? Yes. Okay, and there's one more. It's over here. Okay, what do we see inside over here? I created 3 more surfaces inside of this box, okay? Because these surfaces are going to help us make measurements. So let me just drag it so that it's a little bit more central. Okay, here we go. Need to make it a little bigger. Yeah, and then we'll make it a little easier. Okay. Technical difficulties, I guess we'll make it a little bit. Okay, I think that's good enough. So, let's start with the height of the box. That's just the difference between the outer sphere and the inner sphere. That's your delta rho. Okay. What about this width, or you can call it the length, and width, and what about this over here? Okay, we can call it a depth. Okay, so I hope you see that it feels a lot like 3 intersecting planes. Okay, it's almost like your XY plane, XZ plane, YZ plane. Okay, they are 3 mutually intersecting planes at one point. Okay, which you might think of as the center of that spherical brick. Okay, so what other goodies do I have over here? I have some curves. 1, 2, and 3. Okay, so those curves are basically what look like the x-axis, the y-axis, and the z-axis. Okay, so we are going to take our measurements over there. We already know that the height is approximately delta rho. Okay, what else do I have over here? Click. Ooh, something is on the xy plane. So what have I done here? I have taken this blue curve over here, and that is where your rho is constant. I'm sorry, your phi is constant at the midpoint of phi j minus 1 and phi j. Okay, so remember that when we drop it down to the xy coordinate system, to the xy plane, we get a little arc over there. And guess what coordinate we can measure here? We have your r and we have your theta. Okay, so I have these vectors over there. Woohoo! That helps. There we go. So that is labeled r sub j, I believe. And I'm sorry, r sub I, okay, to be consistent with the rho. Okay, so so let's see. Okay, so we have theta k minus 1 here and theta k over here. So guess what? The angle between them is delta theta. All right, so how deep is the box? That's the same length as up here. We have an arc length. So this is r times delta theta. Is that our next label? Yeah, there it is. Ri times delta theta. Okay, so we can hide those now. Hide, 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 and hide. Okay, so what is our last measurement? Let's see, what was that I was supposed to have? That one. Okay, so our last measurement is this, we can call it a length, I guess. All right, so we want to measure from here to here. I will expose these two vectors. Aha. So those are our phi values. Okay. We have phi j minus 1 and let's see. Well, actually that's the distance. That is our rho I. Okay, but this is phi j minus 1 and hang on, backwards. Okay, phi is increasing from the z-axis, so this is phi j minus 1, and this is phi j. Okay, so this angle over here is delta phi. Okay, so this arc length is delta phi times the radius, which is rho sub I. Okay, so what else do we have? Okay, there we go. So there is delta phi over there. So that arc length is delta phi times the radius rho sub I. All right, so let's continue on page 171. We're going to summarize our measurements that we made over there. Okay, so we have our spherical brick, and we created the midpoint, okay, by constructing the average radius here, and the average cone over here, and the average plane over here. So rho and phi and for theta. Okay, so they intersected at that one point in the middle. Okay, so that's what we had. Okay, so we can see the three surfaces inside, which we expose over here by removing the outer surfaces. Okay, so here are zoom-in views of those three surfaces. Okay, we can see it in different directions. So we needed this measurement and that height, and let's see, this measurement. Okay, so it's a lot like x times y times z. Okay, so we said that the height of that brick, spherical brick, is definitely delta rho. Okay, and then we measured, this was actually the third one that we did. We measured this arc length, which you said is rho I bar times delta phi. And the second one that we did was the arc length on the floor. Okay, so we said let's drop this width down to the floor. We get an arc. That's from your cone. And the angle between them is delta theta, but the radius is Ri bar. Okay, So the arc length is Ri bar times delta theta. Okay, so we need to go one more step. Who is Ri bar? It comes from rho I bar. Okay, we need sine of theta j bar. Okay, so remember the conversion formulas from the last video. Okay, the z coordinate is rho cosine phi, but the radius, when you drop it to the xy plane, is rho times sine of phi. Okay, so we have that length for our brick. We are now ready to multiply the three of them together. Okay, so we have this length down over here. We have the width, which was the rho I bar delta phi. The height was delta rho. So what do? We put all the differentials, the deltas, on the right together. We have a rho I bar here, but another rho I bar here. So we square that, and we have the sine theta j. Okay? So the bottom line, if you were not too thrilled about the last 18 minutes or so, is the dV that we want is rho squared sine phi d theta d phi d rho. Bottom line, that is what you have to remember when we are setting up our triple integrals. That is your d. All right, that was the hard part. The rest of it is basically converting x, y, and z into spherical and remembering to multiply by our dV. Okay, so our x is rho sine phi cosine theta. All right, y is rho sine phi sine theta, and z is rho cosine phi. Okay, so we use our representative point that we plug into our function in three variables. And then we have our delta V ijk. Plug it all in to a horrific looking triple sum. So let me scoot out of the way here. So we have this triple limit of a triple sum of our function times our delta V. You plug in all our conversion formulas into your function, multiplied by our delta V. Okay? So after the dust clears, it becomes a triple iterated integral. Okay, so if it's a brick, it doesn't matter which way we order phi, theta, and rho. If we put rho on the outside, we must go from A to B. Phi in the middle, we should go from alpha to beta. Theta inside, from mu to mu. Don't forget the rho squared sine phi. Okay, just like that extra r in polar coordinates, don't forget the extra rho squared with a sine of phi. Okay, so there's your x, rho sine phi cosine theta, y, rho sine phi sine theta, z is rho cosine of phi. Okay, so let's go to our workroom and we are going to do an example. All right, let's do this. Use spherical coordinates to find the triple integral over e of 5y squared plus 2z dv, where e is the upper half of the hollow sphere, where x squared plus y squared plus z squared is between 9 and 25. Okay, so this is like, we saw something like this in our last video. Okay, you take cantaloupe, right? You cut it in half, okay, and then you orient one of the halves so that it's the upper half of the cantaloupe, and of course you scoop out the seeds because we don't want to eat them, right? So, let's think of our domain E, okay? So we have the equations of the two spheres over here. So obviously our rho is going from our radii are 3 and 5. Okay, and then what? Well, it's the upper half, so we're going from phi equals 0 to the xy plane, which is pi over 2. Okay, so phi is going from 0 to pi over 2. Okay, And then finally, what about theta? Okay, well, you have an entire half cantaloupe up here, so theta can go full circle. So theta will go from 0 to 2 pi. All right, excellent. So we know how to set up the limits of our triple integral. All right, our function is this, okay? So let's apply our conversion formulas, okay? So what is y? We need rho, and then we go to r. So what were we saying? That is our sine phi. And then we use our theta. We need for y sine of theta. All right, so we square that whole thing plus 2z. What is our z? Z is rho cosine of phi. There we go. So, yeah, we can of course simplify that a little bit, I suppose. We can make it 5 rho squared sine squared phi sine squared theta and 2 rho cosine. I guess we don't even need the parentheses over there. Okay, but we will put into our integral. We are going to take our function, and don't forget we are supposed to have an extra factor of rho squared sine of phi. Okay, so look what happened. Okay, because of that y squared, we are going to have a sine squared of phi and another sine of phi. Okay, so we're going to have sine cubed. Oh my! So we're going to get 5, how many rows? Rho to the 4th power and sine cubed phi sine squared theta. So don't forget to change that. And then what about the other one? We need plus 2 rho cubed. So we will have cosine phi sine of phi. Okay, oh my, oh my, oh my. All right, so yeah, how are we going to attack this, right? So I think what I'm going to show you is, because we're doing a spherical break, okay, so rho is going from 3 to 5, phi from 0 to pi over to theta from 0 to 2 pi, okay? And of course, they're independent of each other, okay? None of them is a function of the others, all right? So what we can do is we can integrate each factor one at a time so that, in 3 levels, we can get to the final answer, okay? So let's integrate, let's say, rho first, okay? That seems to be the easiest one, don't you think, okay? So we need integral from 3 to 5. Okay, so we need rho to the 4 d rho. Okay, so this is like the easiest part, right? So this will be 1/5 and then rho to the 5. So yeah, let's go ahead and plug in our limits. 5 to the 5 minus 3 to the 5. Okay, so we are going to get, okay, so that's not so bad. And repeat for rho cubed, of course. So do I dare? We want rho cubed, so we have 1/4. 1/4, 5 to the 4 minus 3 to the 4. Okay, looks fine so far to me. So we get this. Okay, so the new integrand is now going to be, okay, instead of this, we are going to replace. Let's copy that. We are going to replace rho to the 4 with that integral. Oh, so nice. So we can cancel the 5. Ooh, I did not see that coming. And then we multiply this. So we erase the rho to the 4. And then we erase rho cubed, so 13 times 26, 272. Is that right? 272. Okay. Alrighty. So we are down to that function that we need to integrate. Oh, look, there's only one theta. Okay, so let's do that next. Okay, integrate theta next. Okay, so I'm obviously avoiding that bad integral. Okay, so let's see, we need integral of sine squared. Oh, come on, you're experts on that already, right? We are going from 0 to 2 pi. Sine squared is 1 minus cosine of theta, 2 theta over 2. Okay, so that's 1/2 theta, 1/2 of 2 pi. And then the cosine 2 theta, sine 0 to pi, that all goes away. So we get pi. Okay, so what we have now as our final integrand is going to be sine squared phi. So that disappears now and becomes, I'm sorry, sine squared theta. So that becomes pi. So we can put pi in front over here. Now don't forget there's also, this also needs to be integrated. Okay, so there's like an invisible 1 there. Integrate theta, you'll get, integrate d theta, you'll get theta, from 0 to 2 pi. So we have a 2 pi over there. Okay, so 272 times 2 pi, that is 544 pi. Okay, so that is our final integral plus 544 pi times cosine phi sine. Whoops, yeah, put it back. All right, so yes, little by little. Okay, it's just like chipping away at a big granite wall or something. Okay, so this is easy to integrate, of course. Okay, so we have integral of cosine phi sine phi d phi. U substitution, u is sine of phi, du is cosine. So we have u squared over 2. That is going to be a 1/2. Oh, thank you very much. 1/2 of sine squared of phi. And we are going from 0 to pi over 2, right? So yeah, we go from 0 to pi over 2. Double check. That was our domain. Yes, 0 to pi over 2. Sine of pi over 2 is 1, and then minus 0, so that's equal to just 1/2. Okay, so now we save the worst for last. All right, how do you integrate sine cubed of phi? So we may have done a problem or two like this when we did polar coordinates. Okay, so the idea is to borrow. Would you kindly borrow me, lend me a sine of phi? Okay, so yeah, sure. Keep one to yourself, but you are left with 2. Okay, and this is useful because we know our trigonometry. Sine squared is exactly the same as 1 minus cosine squared of phi. Okay, so we can now separate this into 2 integrals. Okay, so the first one we will have, and then we'll have a minus, right? So watch me carefully because I fail a lot when I do this. We have sine squared phi, and then minus cosine squared phi, a sine of phi. Okay, so the sine of phi, everybody knows that. That is the negative of cosine of phi. Quick check, derivative of cosine is negative sine. It will cancel with our minus here. U substitution over here. U is cosine phi. Du is negative sine phi. So we have a negative there already. Okay, so we will have a plus. So that's a u squared du. So we will have 1/3 of u cubed. So cosine cubed phi. Okay, so quick check. We are going from quick check. We are going to check the derivative. So 1/3 cosine cubed phi. Drop the 3, cancels with the 1/3. You're left with cosine squared. Derivative of cosine is negative sine. So we do need the plus 1. Okay, and so we evaluate from phi equals 0 to phi equals pi over 2. Okay, be very careful with the cosine. Okay, because cosine of 0 is 1, not 0. That is where 99% of the mistakes happen whenever you see a sine cubed in your integral. Okay, oh, but cosine 0 is 0. Nope. Okay, so at pi over 2, cosine pi over 2, that's your 0. Okay, so we're going to get 0 minus minus, so plus cosine of 0. Oops. Cosine of 0, and then minus 1/3 cosine of 0. So minus 1/3 cosine of 0. Okay, so that is 1 minus 1/3, which is 2/3. Okay, whew, so what a journey. So our final answer is going to be, we take what we have over here and we do our substitution. Okay, so our second integral, I didn't copy the rest because what one's over here, it's going to be 1/2. Okay, so that's going to be 272. Yeah, that sounds familiar. And then for our sine cubed, we have 2/3. Okay, so we erase this. And there we go. All right, so I think I have everything there. And our final answer is 272 pi. Oh, wait a minute. That's, no, that can't be because we still have the first term there. It's cheating me for some reason. Yeah, there you go. All right. Okay, so yeah, oh look, almost another 40 minutes. Yeah, so it's a lot like when we did polar coordinates the first time. Okay, you need to familiarize yourself with the new coordinate system, another way to view our three-dimensional world. And then you have to learn how to convert your dv. Okay, so that is one of the main lessons for today. Rho squared sine phi, d rho, d theta, d phi, in whatever order you think is convenient. We did rho first, and then theta, and then phi. Yeah, a lot of times phi is the worst. Okay, so it really all depends on you. Okay, you want to get rid of the really bad part first, or you want to start, oh, you know what, I'm going to take care of the easy parts first. Okay, so that's our video for today. This is Jude Socrates signing off. And when I see you next time, oh my goodness, we are going to move on to the next chapter, chapter 4, where we are going to look at a new kind of integral, and they're going to be called contour integrals, and we're going to look at a new kind of function which are called vector fields. So until then, enjoy the rest of your day. Thank you for watching my video. Bye.